All right. And we're live on this beautiful Wednesday morning where apparently Genesis is down and where apparently the school's desktop computer network is down and teachers are not able to access their desktops. It's a good thing that I don't know. I don't teach from a smartboard lesson because most of their lessons are down and they can't access their stuff. Oh, what a morning. What a morning. I'm going to give people a few minutes to kind of filter in as they've been doing so far. It looks like 14. Just double checking something right now. Oh, yeah. Just in case you forgot, you had a minor due about 20 minutes ago, you know, kind of thing. Oh, goodness gracious. It's just been one of those days. That's what it kind of feels like. I don't know. Anyhow, so still only 12 people in there, but of course, the timing is probably a bit off because the laptop says 7:19. Over here it says 7:22. I don't even know what time it is anymore. Anyway, I'm gonna get set up with something over here, and then I'll begin my spiel with some reminders, and we'll kind of go through that, and then we'll see what the day brings us. It's going to be fun, mainly for me. I don't know how it's going to be for you, but it's going to be fun for me. I'm making some, I can't decide if I'm going to have coffee or hot chocolate. I brought the fixins for hot chocolate. I don't know. Hot chocolate seems funner to me right now. But that's me. Most of y'all like, just woke up. Why is there still 11 people? That's so weird. 12 people. There's like 26 in this class. That seems strange to me. All right. Well, I'm going to get started regardless then because I've been on here for a few minutes. So, a couple of reminders before we get moving. Today is Wednesday the 13th. I have you again on Friday the 15th. And then next week is a little weird because you have Monday off. And since you have Monday off, then I will see you again on Wednesday, Friday as well. I'm just saying, hot chocolate's good, you know? Where was I? I lost my train of thought because now I'm thinking about hot chocolate. Yeah, so I have you Wednesday, Friday of next week as well. Next week is when I plan on reviewing for said midterm. Supposedly you guys are going to be back during the week of midterms in my classroom. But of course, that remains to be seen considering where all the numbers are going. The new Cali reports come out tomorrow, which I've been, again, tracking them since August. And this last week's Cali report was higher numbers in a couple of the categories than ever before in this region. So I don't know. We'll see what happens. I don't know. So good morning, everyone. Everyone just kind of throw me a comment in the chat. I just got to see who's here because since Genesis is down, they can't take an actual attendance. Why would they? But yeah, throw a comment into the chat. I already got one thought on a hot chocolate versus coffee. I don't know what's good at 7:30 in the morning, hot chocolate or coffee. You know, you can answer me that way. You know, and I can see your names in the chat popping up. So there's some people there. You know, I don't know. Oh goodness gracious. Sometimes I feel like, just imagine this for a moment. If this whole thing were a computer simulation, and like, what if all of you were fake? And if all of you are fake, what if am I the only one that's real? And it's just me in a room, and this is my existence now. I don't know. I can't lose my mind. If you've already lost. Anyway, so what I want to do today, I want to pick up where we left off last time. Last class, we spent a ton of time talking about geometric probability. Geometric probability, which can be recognized by mainly finding a first success of one sort or another. If you're looking for some kind of first success and the probability of getting that first success on a certain trial or sooner, then you can use those geometric probability functions in the graphing calculator, which is super nice. We learned the formula behind it, which was Q raised to the power of 1 less than the number of trials times P. That would get you the geometric PDF of basically getting failures on all of your previous trials and then getting the success on the trial that you're looking for. The CDF function basically calculates that for every trial, like getting what if I got it on the 7th trial or the 6th or the 5th or the 4th, and it adds all them up for a cumulative geometric function. Again, depending on the wording of the question. But now I'm going to be deep diving a little bit farther. I'm going to be talking about what I've been kind of hyping for a couple class periods now, the binomial distribution. Now, I don't know if you learned this in Algebra 2 or not. I don't know if you learned binomial expansion. Now, I'm not going to get into the details at all about binomial expansion. I'm not going to talk about that at all, other than to say that the principles and properties behind binomial expansion have a direct relation to that of the binomial probability distribution that I am going to be showing you today. It's just really fascinating, the fact that you can have a binomial expansion, something that you learn in algebra, that has a direct link to the binomial probability distribution, which is taught in statistics. Just blows my. But again, going into the details behind why they're connected, that is not the purpose of today. You can look that up on your own time if you get the chance. But what I would like to do, I would like to pick up where we left off. If you do, wait a minute, hold on a sec. I was about to say my line and then I realized something. Blast. This is going to cause a bit of an issue today. I mentioned before that the computers were down, or not down, but the networks were down. Okay, this might fix it. Hold on, this might fix it. Oh, there we go. Excellent. You can't beat me, computer. See, the networks are down. We can access Google Chrome. We can access all that stuff, but all of our files are gone. But I can still access my Elmo camera, and I can still access the calculator on the screen. So yes, I'm gonna need those notebooks out and open. Anyway. This would be the theme song if I had my own show. Of course, I have my own show in my mind, but it's all good. I'm trying to bring up the link for today. Why are you not bringing up the link? I'm trying to bring up the link on my phone so I can see the chat. There it is. For some reason, it wasn't loading properly. Anyway. I hate technology. It's going to rule us one day. It already does. Anyway, today's the 13th. Now I'm going to call this geo/binomial continued, simply because it's just a continuation of the previous lesson, just with slightly different material. So again, I can see what's going on in the chat. I can see all of your names there. I don't know who well, I mean, I can probably figure out by the initials, but MBR. Whatever. Anyway, so a couple things about Bernoulli trials, and I try not to give you too many stars, but this one does deserve a star. Try not to give you too many. Star. There we go. Now this is in relation to Bernoulli trials. Remember, Bernoulli trials, simply put, are trials where the end result is either a success or a failure. If you can distinguish that in describing the trial, then it is known as a Bernoulli trial. If I put the I at the end, now it's Bernoulli. I don't even know. There he is. Anyway, for Bernoulli trials, each trial must be independent from the next. Now, obviously, this comes into play for geometric probability. This comes into play for binomial probability. But if you're doing any type of problem that involves a Bernoulli trial, see if that focuses a little bit better. There it goes. Kind of. If it involves a Bernoulli trial whatsoever, then the trials must be independent from each other. Now, what the direct consequence of that is that the probability of getting success or failure does not change from one trial to the next. If you can ensure that condition, then you can proceed with the Bernoulli trial. You can proceed with either the geometric or the binomial probability that you're trying to calculate. They must be independent from the next. Now, there is a weird assumption going on here. Sometimes you are drawing from a population. For example, let's just say that my population is Barnegat High School students. And I'm just going to make this up. I really don't know if this is true or not. But let's just say that, 15% of Barnegat High School students are left-handed. Let's just say that. I don't know if that's true. I don't care if that's true or not. Let's just say it is for the moment. 15% of Barnegat High School students are left-handed. Okay. Now, if 15% of Barnegat High School students are left-handed, and I begin drawing from the Barnegat High School population, each trial represents a student. So when I randomly select student number 1, there is a 15% chance that they are left-handed. Now, there's only about 1,000 students in the school. Once I draw that student, I'm not going to draw that student again. So I go on to student number 2. Now, because there's like 1,000 kids in the school, drawing student number 2, let's just say there's a 15% chance that that student is left-handed. Now, ultimately, what's going to happen logically is that the more students that I draw from the population, the more of a chance that that 15% left-handed number is going to tip one way or the other. It's like a deck of cards. With a deck of cards, there is a 25% chance of getting a heart. But the second that you begin drawing cards, that 25% chance is altered. So if the first card that I pick is a 10 of hearts, now all of a sudden there's a slightly less than 25% chance that I will draw a heart with my next card. So if I'm drawing from the Barnegat High School population, I'm drawing left-handed, or I'm trying to draw left-handed people randomly. It's like randomly you left-handed, randomly you, or you left-handed. naturally that 15% number is going to sway one way or the other. Now that's contradictive to this statement. The probabilities shouldn't change, and they can't change in order for you to be using Bernoulli trials. That's real life. Statistics is trying to reflect real life. There are certain assumptions and conditions that we have to make in order to complete problems, which brings me to the following condition. There is something called the 10% condition. There is something called the 10% condition. As long as the sample being drawn is less than 10% of the population, then independence can be assumed. Now, I want to repeat that statement. I want to verbally kind of dwell on that statement for a moment, because this is a very important statement. This statement about the 10% condition is going to come back and haunt you much later on in the school year when we are covering hypothesis testing. Hypothesis testing is going to rely heavily on assumptions and conditions to be able to use certain tests within the calculator. So let me read this statement again. As long as the sample being drawn is less than 10% of the population, then independence can be assumed. There are 1,000 students at Barnegat High School. Let's just say that 15% of them are left-handed. As long as the random sample that I draw from the Barnegat High School population is less than 10%, less than 100 students, then, that's less than 10%, then independence can be assumed. Meaning I can still assume 15% chance for each of those people. But if I go over 10%, now I am pushing the boundaries of risking that 15% left-handed number to change. There is a proof for the 10% condition, but that is a bit more advanced than what AP Statistics has to offer. Please keep that in mind. Typically, a lot of people don't even think about the 10% condition. But later on in the school year, when you do your assumptions and conditions for hypothesis testing, you need to list your assumptions and conditions. And if you don't, an AP grader is going to rip your throat out. Yes. So let me go to the deck of cards. I got 52 cards here. 25% of them are hearts. If I randomly draw cards from this deck of cards, as long as I draw less than 10%, meaning 5 or less cards, then I can assume independence. It's only 5 or less cards then. I can assume a 25% chance for each of them to be a heart. But if I go over 10%, that assumption now falls apart, and I can't do it. A lot of people, they hear that word assumption, and they're like, ooh, I was always taught never to assume. You have to assume. In statistics, there are a lot of assumptions that you have to make because real life doesn't always reflect the perfect and ideal situation. And because of that, you have to make certain assumptions and conditions within reason. I've always heard that when you assume, you make a bad word out of you. And that's not a good thing. Why would you make a bad word out of you if you're going to assume? Just saying. Anyway. Next. Let's talk about binomials. Let's talk about binomials. Okay. Now, I'm going to be drawing something on the board for this. So I actually, well, do I want you to put it into your notes? Yeah, I guess I do. I guess I do. Okay, fine. I'm going to give you the definition of this first, and then I'm going to give you an example that I'm going to kind of put into our notes. And then we'll see where it goes from there. This is the binomial model. Now, again, the binomial model, the reason why it is called the binomial model is because of that direct link to binomial expansion in algebra. But again, I'm not going to get into the details of that just yet. For a binomial model, you can recognize a binomial model because the problem will be describing something like getting a certain number of successes within a finite number of trials. A binomial model can be recognized when the problem is describing getting a certain number of successes within a finite number of trials. Whereas with a geometric problem, you were looking for the probability that you would get a first success on a certain trial or sooner. With a binomial model, it's getting a specific number of successes within a finite number of trials. So for example, my parents were going to have 4 kids. Let's just say they were. I don't know if they were actually planning on that personally. I think I was a mistake. But let's just say that my parents were going to have 4 kids. Now, clearly, the makeup of those 4 kids as they're born are they're boy or girl. Now, some people would argue for not a 50-50 chance, but for the sake of simplicity, let's just assume a 50-50 chance, okay? Because we're trying to relate this to a binomial model. So 50% chance of a girl, 50% chance of a boy. Within a Bernoulli trial, of course, we are talking about successes versus failures. Now, just so you know the makeup of my family, I am one of 4 kids. I am the only boy. I have 3 older sisters. Number 1, feel bad for me. Number 2, if you are going to be defining a Bernoulli trial in the context of my parents having 4 kids, you have to define a success and a failure. Not that I would define my parents having a girl as a success, me as a moving. Now, in the 4 kids, anything could potentially happen within that realm. You could have boys and girls in any particular order, but there are a finite number of possibilities if you're going to do that. For example, if I was going to describe the 4 kids that my parents had, there was a possibility that it could have been girl, 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 girl. And yes, I would like you to write this down simply because I want you to see what this thing ends up being. Now that's having all girls. Now what if there was one boy? It could have been girl, 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 boy, I guess. Yes. However, me being the youngest, that's my situation right there. But what if the boy was the 3rd kid? Because you could have girl, girl, boy, girl. That is also a possibility for 4 kids. So you have to take birth order into account, or specifically the individual trials into account. Ooh, okay, hold on. Girl, boy, girl, girl, boy, girl, girl, girl. Those are all of the scenarios in which there is one boy. Now, what if there were two boys? All right. Again, this is not what my family had, but let's just see what happens. So it could be girl, girl, boy, boy. It could be girl, boy, girl, boy. Y'all see that? Yeah, it's just outside the glare. I was trying to avoid the glare. There we go. It could have been boy, girl, girl, boy. It could have been girl, boy, boy, girl. It could have been boy, girl, boy, girl. It could have been boy, boy, girl, girl. Those are all the scenarios with two boys and two girls. Now, what if there were three boys? Let's just see. Girl, boy, boy, boy. Boy, girl, boy, boy. Boy, boy, girl, boy. Boy, 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 girl. And then, of course, there's the possibility of all boys. Boy, 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 boy. So altogether, what is that? 6, 10, 14, 16. There are 16 possible outcomes. 16 possible outcomes for my parents having 4 kids and the makeup of being boys or girls, depending on the birth order, the trial that had occurred. Now, the specific situation that happened in my family was this. Now, if I were describing, now listen very carefully, if I were describing a geometric problem, if I were describing a geometric problem, I would describe it in one of two ways. I would say, what is the probability that my parents would have a boy, their first boy, on the 4th trial? Then this would be the only scenario that we're looking at. 50%, 50%, 50%, 50%, the whole thing. But if I was saying, what are the chances that my parents would have that first boy on the 4th kid or sooner? Now, that's a different scenario. That doesn't involve all of this, because all of these are assuming 4 children. Because if you have that first boy on the 4th trial or sooner, then once you get to that, let's say 3rd trial, oh, it's a boy. You stop. Or the 2nd trial, oh, it's a boy. You stop. You don't go any farther beyond that with geometric. With geometric probability, the number of trials that actually end up occurring, it's not set in stone. Whereas with a binomial model, it is. A certain number of successes within a finite number of trials, and the trials here are 4. Now, if I'm looking at all of this, technically, and this doesn't happen for every problem, but technically, each of these lines have an equal chance of happening, because this is 0.5 times 0.5 times 0.5 times 0.5. That's like 1 over 16 or some junk like that. Which, of course, there are 16 of these things. Yay! In this particular instance, the chances that my parents would have one boy is actually 4 out of 16. I'm going to show you these formulas in a little bit. It's very strange. Go to your calculators. Go to your calculators. Because I'm going to show you how this all relates. So first, chapow. Oh, come on, diagnosis, cancel. Come on. Nope, that didn't work either. There we go. Nailed it. First try. If you hit second vars, if you just type up, it'll take you down to the bottom. But I'm interested in binom PDF. Binom PDF. And when you go into binom PDF, this is a binomial PDF, probability distribution function, or probability density function, depending on who you're talking to. Number of trials. There are 4 trials for the 4 kids. The probability of success is 0.5, 50% chance of having a girl. The X value, or boy, I should say, that for once in my life, let me be the success. So but the X value, let's make it a 1. So there's 4 trials, a 50% chance of having a boy, and I'm looking for the probability that they will have one boy within those 4 kids. 25% chance. Now let me do this one more time, but let me do it with 2 boys, and I'm going to compare it to all of the letters that we just wrote out. So let's see, second, vars, binom PDF. Let me change it to 2 boys. 0.375. Let me go back to my notes real quick. Let me just check that 0.375. There were 16 possible outcomes for boys and girls. And there were 6 situations in which you would have 2 boys. Okay. 6 out of 16. Now, I mean, this is kind of anticlimactic at the moment because obviously you know what's about to happen. Oh, 0.375. That's what this thing does. What the binomial model does is it will calculate all of the possible scenarios that we just wrote out on paper. That's what it will calculate. It will calculate the probability of successes and failures within a finite number of trials. Now, I simplified this greatly. I simplified this greatly because each of these probabilities was 0.5. They are not always going to be 0.5. They are not at all. Let me show you what this thing entails. So I'm still working with a binomial model. I'm back in my notes. First of all, N is the number of trials. N is the number of trials. P is the probability of success. As always, Q is the probability of failure. And because it is a Bernoulli trial, those are the only outcomes, success or failure. X is the number of successes. So, for a binomial, a binom, the probability of an event happening is equal to the following calculation. Now, write this down exactly as I write it, and then I will explain what each component actually is. Make sure it's not in the glare. It kind of is. Move it down a little. Move it down a little. I'm just trying not to get it in the glare. Okay. For a binomial, this is how the probability is calculated. The probability of the event. Well, first of all, the probability of success raised to the x power. Now, in this instance, hold on, where's my marker? Probability of success in this case is 0.5. Let's say that my parents are looking to have one boy. So let's just say that's the success that they're looking for. So in this case, this would be 0.5 raised to the first power. And because Q is also 0.5, it's just a coincidence that does not always happen. The probability of failure and success don't always match each other, but it would be n minus x, which in this case would be, well, 4 minus 1, which is 3. Now that takes into account getting the boy, which is 0.5, and getting the girl, which is 0.5, 0.5, 0.5. But as I demonstrated earlier, It can happen in any order. That one boy could be born first, second, third, or fourth. And because of that, this is utilized. This is what is known as a combination. This is what is used to actually construct certain numbers within the binomial expansion of algebra. It's very strange. This, I don't know, some of you may or may not know this. I don't know if anybody is familiar with Pascal's triangle, but Pascal's triangle is constructed using that combination function. Now, that combination function will give you the number of ways certain things can happen. For example, let me go back to the calculator real quick. Click. You actually do have a combination function in the calculator. If you hit math and tab over to prob, the third one down is known as NCR. And NCR, in this case, if I do 4C1, it spits out a 4. And what that is actually calculating is, well, I have 4 objects to choose from. And I only want to choose one of them. I have 4 aces to choose from, all different suits. I only want to choose one of them. It's more interesting when I change that 1 to a 2. Because think about it, how many different ways were we able to get 2 boys? Well, there were 6 different ways. Yeah, of course there were 6 different ways. We wrote them out. That's how it was calculated. What this function does in connection with our notes right here is it figures out the number of different ways that particular event could happen. That number of successes, okay, well, how many different ways could it happen in that order? And then it uses that to calculate the probability. Now, a couple things to it. First, you may end up seeing it expressed like this. You may end up seeing it expressed like this. It may look like this when you do a problem. Let's say like a multiple choice problem. This is just another way of writing it, another type of notation. There's no fraction bar between them. It's just a floating n and a floating x, and it means a combination. I wish I can go into way more detail about this because this function is so vital across the spectrum of mathematics. But again, that's not the purpose of this lesson. The purpose of this lesson is to get into the binomial. Just for the sake of argument, in case you were interested, the way that this is actually calculated is like this. For those of you who understand factorials, that's actually what is being done to calculate the number of ways that event could actually happen. Very strange. Very strange. Again, not getting into those details. That's not the purpose of this lesson today. The purpose of this lesson today is to get into different details of binomial problems. So, for example, let's go back to our left-handed person problem. If I was doing a left-handed person problem in Barnegat High School, again, we've talked about it. Yes, there's 1,000 kids in Barnegat High School. As long as I stay under 10%, I can assume independence. So let's just assume that. So left-handers at BHS. Let's say the probability of success is 15%, 0.15. Okay. And let's say that I have your class. And your class, according to my roster, has 26 students. All right. 26 students. Oh no, my Phone's falling. Here we go. So I'm going to let n equal 26 being the number of trials because I am getting assigned 26 students into my classroom. Now, I'm assuming 15% of you are left-handed. I'm sorry, of the population of Barnegat High School is left-handed. My bad. But with 26 of you, I don't know. I wonder, what is the probability that out of my 26 students, so what is the probability that I would have, because 15%, that's not that many students. It's like 3 students, maybe. What's the probability that I would have 10 lefties? What is the probability that I would have 10 lefties? Now, again, there's 2 ways of actually calculating this problem. One way of calculating this problem is by utilizing the binomial function and all of the numbers that go into it. There we go. And I could type that out by hand, which I'm going to type out by hand just as an example. But the probability of 10 lefties out of that 26, well, 26C10, which I'm going to type out, I will. Probability of success raised to the power of the x value that I'm looking for. Oh, I forgot I left that 0.5 on the board. Times 0.85, which is the probability of failure raised to the 16 power. The 2 exponents together, 10 and 16, should be the number of trials. And they are. So let me see what my calculator does here. Click, parentheses. Let's see, math, NCR. Put a 26 there. Let's put a 10 there. Okay. Let's close out that parenthesis. Times 0.15 to the 10 power times 0.85 to the 16 power. Good. Now, you're going to love what the calculator does in a moment, but you need to know the structure. You don't have to calculate this by hand. You can use the binomial function in the calculator to get this done. That's not a problem. But you need to understand the structure of this equation. Let's see what happens. Boom! 0.0023. I'm going to write that down. 0.0023. But now, let me show you how much easier it is if you simply did second vars binomial PDF. I talked about the difference between PDF and CDF last time. I'll talk about that more today. There are 26 of you. A 15% chance of success getting a left-handed person. And I'm looking to get, well, what are the chances that I would have 10 lefties in my room? Just 10. Oh, would you looky there? I mean, at this point, there should be no surprise that I'm right. Because I'm a genius. But that's just the way it rolls. So going back to my notes real quick, I'm just going to write out what that thing was in that order. You could calculate a binom PDF of 26.15, 10, and it will spit out that answer. A binom PDF of 26.15, 10. That is the order that you do have to type that thing in if you don't have the interface that these calculators have. Very strange. Very strange. Let's go into more details. First of all, PDF versus CDF. Once again, binom PDF versus binom CDF. Zoom in. There we go. This is the probability of getting exactly X successes. It's the probability of getting exactly X successes within those finite number of trials, of course. Whereas CDF is cumulative. It is the probability of getting X or less successes. And I'll go back to our left-handed example in the calculator in a moment, so I can show you the CDF calculation. Binom CDF, 26 trials, 15%, 10. Now, because I'm doing the binomial CDF, once I hit enter, this will calculate the probability of getting 10 or less successes, meaning it will calculate getting 10 successes, 10 lefties, or 9 lefties, or 8 or 7, all the way down to or 0, because there is the possibility that I could have 0 lefties in the class. Well, yeah, there's about a 99.9% chance that I will have 10 lefties or less. That simply makes sense. I wonder, how many lefties would we expect out of 26 students? Go back to my notes. For a binomial, the expected number of successes, it seems very logical at this point, but it's just n times p. The number of trials times the probability of success. So if I did 0.15 times 26, 3.9. Out of 26 students at Barnegat High School, I would expect, on average, about 3.9, 4 if you want to round it, whatever. But approximately 3.9 students to be left-handed in a group of 26 students. Obviously, if the number of trials change, the number of successes or expected successes change. There is also an expected standard deviation. And now this one, you do need to know this formula. There's an expected standard deviation from a group of 26 to a group of 26. It is the square root of n times p times q. That would be the expected number, or the expected standard deviation, I should say. The way that that problem works out, it's so wonderful. It's so wonderful. It just is. Now, like I said, this does come into play heavily later on in the year. I'm going to show you something on the computer. I believe I can still access Chrome even though the network is down. Let's see. Close that. Open that. 2019 AP Stat. Pre-response questions. Boom. Here is the formula sheet that they give you on the AP test. Can I make this bigger? I'm going to make this bigger. Can't see it terribly well. But on the second page, and I've shown you a little bit of the second page. I've shown you a little bit of the second page. I've shown you these top two formulas where it's like the probability of A or B and the probability of A given B. But they also give you how to calculate expected value, the sum of the x quantitative or the numerical value times the probability of it happening. And they even show you how to calculate the variance, which of course is just standard deviation squared. But then they give you a bunch of these formulas right here. Look at this junk. They give you the binomial formulas, which is nice. You don't have to memorize them, but they're there. You have to know how to use them. Instead of Q, they give you 1 minus P. They give you the expected value of a binomial, and they give you the expected standard deviation of a binomial. These formulas we are going to learn in due time. We're going to learn the rest of these formulas after midterms. But they do give you the 3 important formulas in regards to a binomial distribution. They don't give you geometric, but they do give you binomial, which is nice. Just want you to be aware of that. A lot of these formulas, they do give you a lot of these formulas, they just expect that you know, which is just myrrh. Anywho, so here's what I'm going to do. Obviously, we still have Friday. On Friday, we are going to get some practice with geometric and binomial problems. We're going to get some practice with that. Obviously, you're going to be using your calculator to get a lot of those things done. You had a minor due for me today at 7. It looks like not everybody turned it in. I don't know. I haven't looked at the individuals. I just looked at the numbers. But get that done if you haven't already. On Friday, we're going to get that practice with binomial geometric, the differences between them and things of that nature. Probably going to assign you one more thing before we begin reviewing next week. Next week, we are going to begin reviewing for midterms, going back to the beginning of the year. And we'll kind of see how that goes. Anyway, that's it from me. I know I'm a few minutes ahead, but because of the network issues that we're having, I do need to get some things ready for the rest of my day because I teach straight through. And with the network being down, it's going to be so much fun. If you haven't already left a comment in the chat, please do so, because with Genesis being down as well, they're tasking me to take a paper attendance. Just like, okay, dude, whatever. But please make sure that you have commented in the chat so I can do that appropriately for people in the office. And in the meantime, I am going to dismiss you a few minutes early, like this is a college course, and I'm going to be like, go wander the quad, go get a cup of soup in the student union, which, by the way, was one of my favorite things to do. I would love just to get soup on a cold day. I forgot to make my hot chocolate. Okay, I'm going to go do that then. No, I do have to get ready. Anyway, I'm going to sign off. You guys can go. Bye-bye, bye-bye. Take your stuff with you. Bye-bye, bye-bye. I'm going to shut off the stream in a moment. Bye-bye, bye-bye. Don't leave your stuff under your desk. Bye-bye, bye-bye.